The next person who's going to present is Diego Sanchez, and Diego is an undergraduate student at Essex County College. Also does work in, he also works with us at MJIT, and so I've been working with him for about 2 years now, and he's also working with Gareth as well, and he's going to be looking at traveling ionospheric disturbances using reverse speaking network and WhisperNet data, and some of the techniques that you see in his presentation are also going to be comparing that data to TEC data. So you'll see the TEC data again, and some of those techniques we're going to try and extend them to higher latitudes to see if we have the ability to help answer James's question as well. So go ahead, Diego.
Hello, can you hear me?
Yes, we can.
Cool. So I hope everyone's doing well. Let me share. Go. Can everyone see my screen?
Looks good, Diego. We can see and hear you.
Yes, we can.
Good. Yes, so I'll be giving my talk, parting the very long title, Large-Scale Traveling Ionospheric Disturbances Observed Using HamSCI Amateur Radio, SuperDARN, GNSS TEC, and Ionosondes. So like Nathaniel said, this is a continuation of our work, and a lot of stuff I will be talking about here will have already been reinforced in past talks, so I'll go quickly. So traveling ionospheric disturbances, they are quasi-periodic variations of F-region electron densities. There are different types. We're primarily going to be looking at large-scale TIDs, so anything greater than 1,000 kilometers wavelength. And primary data sources that I used for here, ham radio, reverse beacon network, and weak signal propagation reporting network. The majority of our plots, it tends to lean more towards WhisperNet data instead of RBN, but we also use SuperDARN, the GPS TEC, NASA Omni data, and FOF2 data from Ionosondes. All right, so this first image is just showing what happens to HF propagation when the ionosphere is perturbed, and you could see as the ionosphere becomes perturbed, the distance refraction decreases, and therefore the distance of the transmission increases. And to show. This is a simulation using of SuperDARN of how a TID would be imaged with SuperDARN. So we could see. Can everyone see my cursor?
Yes.
Okay. So we have image A here. The various beams of a SuperDARN array. In this case, the Fort Hays East, and we're focusing on beam 7 right now. And in the background, you could see the simulated perturbed IRI ionosphere. In the middle image, you could actually see, now let's see if this works. No, apologize for that. This is supposed to actually be a movie. But yeah, this middle image here would have shown the change in the distance of the HF ray as the ionosphere changes over time, and you see that as the backscatter power, the power strength, the high backscatter power strength, as the ranges change, that's how the ionosphere is actually. The refraction through the ionosphere is changing over time. So this is how we would actually see the TID represented in a SuperDARN plot, as we could see in this next one here. So this is for the 3rd of November, a TID that was going through, and we have 3 very distinct wave structures, or peaks in this case, these plots, we can see the slant range, the backscatter power on the right-hand side, and UT time on the bottom. And this is an example of the TID plots that Nathaniel has been making. So first, down here, this is the actual plots using the ham radio data. We have the range of the spot, the distance from transmitter to receiver. On the right, the density, the spot density. So every, you can see color coded, the more yellowish is the higher spot density that there is at that given moment. And we were primarily looking for geomagnetically quiet and solar flare quiet days. So that's these two top areas up here using KP index and SIM-H and the GOES X-rays. Now, November 3rd, we have fairly quiet. So these wave structures that we see through the TID data over here, it's very probable to be a TID. Now, we took this and compared this to the GNSS TEC data. So the shorter the range that we see in the ham radio data would correlate to a more total electron content. Therefore, refraction would increase, and we would see that here. This is a movie. This first section from 1500 hours to 1800 hours, you'd see an initial blueing of the area, and then back as the ionosphere becomes more charged, we'd start to see more reddish colors. So I'll play this real quick. Not as noticeable, but you see more bluish colors as it's coming out down here through the wave. And then back more red colors as it comes here towards 1800 hours. So we actually see the wave structures that we're seeing in the ham radio data is actually lining up very well with what we're seeing with the GNSS TEC data. And one of the primary focuses that I've been doing recently was finding other days with potential TIDs in them. And this is one of the candidates that I found November 23rd, 2017, and comparing this with GNSS TEC data. So we could see here these first waves. And I have the next slides taking specific spots at each of the peaks and just showing the change in the total electron content with the TEC data on the right-hand side. So we start off, 530, and as we go, the distances are increasing in the ham radio data. Therefore, presume that the ionosphere, total electron content of the ionosphere is actually decreasing, and we could see that in a change here down as the areas become more blue. So it goes, more reddish blue, and then as we come up to another peak where the distances have decreased, it becomes red again in the TEC plot, indicating again increase in total electron content, and then back to blue. And we also found this for a second day that I found, January 26, 2017. You see these two major waves. And again, first indent, as we reach the peak, this one's way more dramatic. We see a much sharper decrease in the range of the spots. And we see a much greater change in total electron content. And as we expect, as the distances increase again, we would see a decrease in total electron content. And then again, as distances decrease, an increase again in TEC, total electron content. Now, another data set that we've been comparing to using Ionosondes, tried to find or use Ionosondes that were relatively close to larger concentrations of the radio spots. So you could see up here, the one for our European plots, the Julius Rue in Rügen, Germany, relatively close to the concentration. Sorry. And in the US, using the Boulder Ionosonde in Colorado. Now, I primarily using the FOF2 data from the Ionosondes. So FOF2 is the highest frequency that the ionosphere reflects back to the Ionosonde. And so we expect the higher the frequency that is bounced back from the ionosphere, the higher the electron density would be. And we could see that the two plots, our ham radio plots, line up very well with the Ionosonde data. So the higher the FOF2 frequency would correlate to a higher electron density in the ionosphere, therefore a decrease, more refraction and a decrease in distances between transmitter receivers with the ham radio spots. And then again for September 27, we see this time over Julius Rue in Europe. Again, they line up very, very well, same times. As the FOF2 values go up, we see a decrease in the actual distance of the ham radio spots. So basically finding that ham radio, they're very coherent across the continental US and Europe, where the majority of our spots are. Very consistent with SuperDARN, GNSS, the TEC data, as well as the Boulder and Julius Rue Ionosonde data. RBN and WhisperNet can serve as tools for monitoring LSTIDs day and night. However, the majority of our spots were from 14 megahertz and not 7, primarily using 14 and 7 megahertz spots. But 14 megahertz would kind of, we barely would get any data for nighttime. And yeah, from here, trying to find out what is the actual source of these detected LSTIDs. So, any questions?
Thank you so much, Diego. Yeah, so are there any questions?
Oh boy.
You're doing great, Diego.
Thank you.
Let's see, Jonathan Rizzo, my other student here who's presenting tomorrow, he says, is it possible that sudden ionospheric disturbance data from monitoring phase and amplitude of VLF transmitters might be useful in detecting MSTIDs? I'm not sure. Phil, do you have anything?
VLF transmitters are normally often, I mean, these are these are lower frequencies. They have very, very long paths, usually reaching between one hemisphere and the other one along magnetic field lines. The signal for, yeah, the signal might be pretty weak for an MSTID embedded in the VLF signal, but I'm guessing here.
The other issue might be that VLF doesn't get very high into the ionosphere. It probably doesn't get up to the F2 region at all.
Well, actually, it will leak out of the higher latitude portions of the ionosphere and end up in the other hemisphere. The Stanford group in the 1960s worked on that. The difficulty is that it's kind of something like Carl said, it actually goes through the ionosphere pretty fast. I mean, it's of its long path, only a portion of it is in the ionosphere. So that would be my thinking on that one. By the way, Nathaniel, we have one more question that's actually in the Google Doc. This is from Dr. Liz McDonald, who says, "Great talk, by the way." There you go, Diego.
Thank you.
She says, "What would be your ideal number of observers to quantify the large-scale TIDs? Do you need more or stronger events? What would be on your wish list?"
I mean, from all the plots that I've made, it seemed it varied. Sometimes I would get very pronounced or very observable TIDs with like less than 60,000 spots, but then other times have a known TID with over, for example, 300,000 spots and not be as defined. So I'm not actually sure.
Okay. Yeah, it's a really good question, and it's one I know Nathaniel and Diego and I have. I specifically remember a long ride from Hamvention last year back to New Jersey, where we talked about, how many spots would you need and how many receivers would you need, and whether or not we could simulate it and stuff. It's a really good question. I think some of the interesting stuff that I think Diego's examples of Central Europe really show about the value of a density of spots, in my opinion at least. But then, as Diego says, you get those odd cases where you don't need as many spots and you still can pull out the structure. So it's a really interesting question to me, at least. It's a good question, a good thing to look at too.
I think something for the ham radio evangelists out there. We need. I think the thing over the U.S. and over Europe, we have pretty good coverage. And actually, I have a copy of Diego's presentation here, so I'm gonna
just move back to. Sorry.
Let's see. I was gonna say go to your slide. Just go to your slide 20.
20.
I'm gonna play with the annotation tools here. Actually, go to the next slide because it shows both the US and Europe. Okay, right. So like, you can see how there's so much more spots over on the east coast of the US than there is on the west. So certainly trying to get a little bit more spot density out here, I think would help. You can see how concentrated everything is over Europe. So one thing so we're thinking that this is where our instrument, if you were, is most sensitive. So I think trying to get more distributed receivers in other parts of the world to increase the observations, even down in Africa and in Russia and all these other places, and then trying to get more ham radio operators out there participating in WhisperNet or CW contests or the PSK networks, trying to get this sort of coverage in more parts of the world would be a really big deal and would really help us. So Tim Duffy and Ward Silver, if you're out there listening, if we can do things to motivate more people to become ham radio operators and set things up to increase the coverage of this on a more global nature, I think that would really help the case.
I will point out also that the South Africans have a particularly strong amateur radio society, and Nathaniel and I have been contacted before when they noticed the HamSCI collective, a year or two ago. And so there are places where there are already people seeing if they can sort of contribute to this. So we have footholds in various other places which don't have a lot of coverage right now. And as Nathaniel said, a good idea would be to try to expand those.
All right, thank you very much. Well, we are up to our last presentation.